Welcome to the part 1 of array implementation of stacks. In this presentation and in the subsequent presentations, we will look into the array implementation of stacks. If you remember in the previous presentation, we have seen the stack as an ADT, that is abstract data type. This simply means that we are looking into the operations of stacks from the user point of view. Now we will look into the implementation details of the stack. So without any further delay, let's get started. Here is the outline of this presentation. We look into the two most important operations, push and pop of stack. And in this presentation, actually, we'll look into the basics of push and pop operations. Okay, so there is nothing to wait. Let's get started. A stack is a linear data structure in which insertions and deletions are allowed only at the end, called the top of the stack. We are aware about this, that stack is nothing but a linear data structure, but it has a restriction. Here insertions and deletions are allowed only at the end, which we call the top of the stack, right? As a stack is a linear data structure, we can implement it using an array or a linked list. Isn't that so? We know that array and linked list are linear data structures. So stack is a linear data structure and we can actually implement it using an array or a linked list. In this presentation and in the subsequent presentations, we'll see the array implementation of stack. Later on, we will also see the linked list implementation of stack. Now I just want you to focus on the array implementation of stack. Now here is how the array looks like. Obviously this is an array. Here you can see the capacity of this array is 6. This means that this array is capable of storing 6 elements. As you can see, there are 6 boxes available, right? Here each cell or a box is capable of storing some value, some integer value maybe, because I am assuming that this array is of type integer. Okay, you can see the name of this array, quite an interesting name, stack ARR. To be precise, this is stack underscore ARR. I just want this array to behave like a stack, that's why I have chosen this name. Okay, we know that stack ARR is an array and insertion and deletion operations can be performed at any place. At any place, we can perform insertions and deletions at any place, right? Because this is an array, we can perform insertion at index 2. We can perform insertion at index 5. It is possible. We can delete a particular element at particular index. Maybe we want to delete an element at index 3. It is possible, right? So we can perform an insertion operation and a deletion operation at any place. But we want the stack ARR to behave like a stack. Isn't that so? Obviously, we want this array to behave like a stack. That is why it is important to allow insertions and deletions only at the end of the array. For this, we will keep a variable top, which will keep track of the last inserted element or the topmost element in an array. That's why we are in a strict need to keep a variable top, which will keep track of the last inserted element. Okay, let's say the last inserted element is at index 3. Therefore, top variable will store the index value 3. Fine. This means that the last inserted element is at index 3. As simple as that. That is why we are keeping a variable top, which will keep track of the last inserted element or the topmost element in an array. Okay, let's move on. Now, in order to indicate that the stack is empty, we will put -1 in the variable top. So in this particular variable top, we will put -1 to indicate that the stack is empty. You can see that currently stack is empty. There is no element in the stack. That is why we are storing -1 in the variable top. Obviously, we want to store some value which is not a valid index, which simply indicates that the stack is empty. Obviously, here you can see that 0 is the valid index, 1 is also the valid index, and so on. These are all valid indices, right? Here we want to store some invalid index to indicate that the stack is empty. That is why I am storing -1 over here. You can choose some other value also, maybe -2, maybe -5 or something like that. I have selected this value -1 and there is a reason behind this. Okay. Later on, we have to increment our top by 1 every time. Now, if we increment the top by 1, then it will get replaced by 0 and 0 is a valid index, right? And incrementing the top by 1 simply means that we are about to store some value in the stack, right? So if top is 0, this means that the topmost element is at index 0, right? So it makes sense to store -1 to indicate that stack is empty. Okay. Please note that top equal to 0 indicates that the topmost element is at index 0 and this means there is only one element in the stack, right? Obviously, if top is 0, then it means that the topmost element is at index 0 and there is no element above it, right? And this simply means that there is just one element in the stack and that particular element is at index 0. For the push operation, top has to be incremented by 1 and new element must be pushed at the position top. Isn't that so? First we have to increment the top variable. That's why I've told you that initially we have to increment the value of top. Then after that we can push the element at that particular index. Isn't that so? This is important and this order is important. We cannot push the new element at the position top right now because top is -1 and it is not a valid index, right? First we have to increment the top. Then after this we can push the element at that particular index, right? You can see this that for the push operation, top has to be incremented by 1, then the new element can be pushed at the position top, right? So what do we mean by this? First, let's increment the value of top. You can see the top is replaced by 0 because -1 plus 1 is 0, right? After incrementing the top, we can push the new element at the position top. You can see that 1 is pushed at this particular position. Here we are interested in pushing value 1. That is why you can see that 1 is pushed at this index 0. Now it is easy. We can perform some series of push and pop operations. Right now we are interested in performing push operations only. Let's try to push 2. First we have to increment the value of top. It becomes 1. Then at this particular index we will store this value 2. What is index 1? You can see this is index 1. Let's store this value 2 over here. After this we have push 3. Push 3 means first we will increment the value of top by 1. Then we will push the value 3 at index 2. Simple. After this we have push 5. Which means that first we will increment the value of top by 1, then we will push this value 5 at index 3. Simple. Now we have push 10. Push 10 means push this value 10 at index 4 of course because top has to be incremented by 1 first and then we'll push that element at index 4. Now we have push 11. Push 11 means that first the top has to be incremented, which means 5. Obviously top equal to 5 means that topmost element must be at index 5. So let's just store this value 11 at index 5. Simple. Now I think the idea is clear. Okay, the stack is full now because we can see the capacity of the stack. It can store at most 6 elements, right? Now we are interested in pushing this element 12. Obviously first top has to be incremented and then we can push this element inside the stack. But wait, the capacity of the stack is 6. That means it can hold at most 6 elements, right? It cannot hold more than 6 elements. Right now the stack is full, therefore it is not possible to actually put this element inside the stack. There is not enough space in the stack. The state is called the overflow state. Please remember that this state, this particular state, when the stack is full is called the overflow state and the new element can't be pushed. Okay, we cannot push the new element. That's why it is called the overflow state, right? Now we are interested in performing this operation. Instead of doing push 12, we are interested in performing this operation pop. Now what do we mean by pop? For the pop operation, the element at the position of top is deleted. This is the first thing. Obviously the element at the position of top must be deleted. And then after this, the top must be decremented by 1. Simple. We cannot decrement the top first. We first have to delete the element at the position of top. And then after this, we can decrement the value of top. Simple. This is how the pop operation can be performed, right? Now first the element at the position of top is deleted, which simply means that we will delete this particular element, that is 11, and then after this the top is decremented by 1. We'll decrement this value by 1, which means that it becomes 4. Now this simply means that the topmost element is at index 4, and you can see this, the topmost element is at index 4, right? So in this way we can perform the pop operation. Let's say we are interested in performing the pop operation once again. And in that case, obviously we know that top is 4, which means the topmost element is at index 4. So we'll first delete this element and then we will decrement the value of top by 1. Now this means the topmost element is at index 3. I hope it is clear to you how we can perform push and pop operations in stack, right? It is very simple. Now it would be easier for you to write a C program equivalent of this particular logic, right? This means that we can perform push and pop operations in stack. And obviously we are representing a stack with the help of an array. And that's what we will do. We'll try to write an equivalent C code which can perform push and pop operations in this particular array. Okay friends, this is it for now. Thank you for watching this presentation.